In the borehole, a transmitter, energized with a constant alternating current, induces a secondary current in the formation concentrically around the borehole. This induced current moves in ground loops about the borehole and logging tool. The secondary current, in turn, induces a response in the tool's receiver coils.
In actual tools, service companies have added extra transmitter and receiver coils to the idealized two-coil model as a means of achieving focus on certain regions of the formation and to minimize the response from the near wellbore area and from shoulder beds. Since horizontal and vertical focusing of the measurements is possible, it follows that, like electrical resistivity tools, induction devices can be configured for dual functions with multiple transmitter and receiver coils.
With more than one measurement being made by a single tool, we can solve for more than one unknown, as we did with multiple electrical resistivity devices. Again, we are able to determine and solve for the formation resistivity, R sub T, the diameter of invasion, D sub I, and the flushed zone resistivity, R sub XO. The magnitude of the induced secondary current and the response measured by the tool depend on the conductivity of the formation. The higher the conductivity, the larger will be the secondary current and measured response. The direct measurement made by the induction tool, then, is one of conductivity.
This measurement is expressed in millimos per meter and in resistivity units, ohms meter squared per meter, to match the presentations on resistivity logs.
As with electrical resistivity devices, corrections for downhole environmental effects and borehole conditions are necessary. One correction is for skin effect. This term is used for interference and secondary currents that develop among the infinite number of ground loops within the induced magnetic field. The net effect is to reduce the returning current signal received by the tool.
The magnitude of the loss plotted here shows that as the conductivity of a formation increases, the skin effect becomes more pronounced. Consequently, the returning current signal at the tool will be progressively diminished with increasing formation conductivity. However, compensation for skin effect losses is now automatic. The corrections for bed thickness are carried out with charts. By plotting bed thickness against measured resistivity, an improved resistivity of the center of the bed is determined. Other corrections for induction logging include hole signal and effects of drilling filtrate invasion.
Like most logging tools, the induction has a two-point calibration.
Since the measurement is one of conductivity, the tool is first placed in a zero conductivity environment and should measure zero conductivity or infinite resistivity. Now, when an artificial formation of known conductivity is introduced and placed about the tool sensitivity can be adjusted to measure its value. After these two endpoint measurements are made, the tool response will be able to reproduce conductivity and inversely resistivity measurements found in most formations. Since this procedure is somewhat cumbersome at the well site, calibration resistors in the tool reproduce the values obtained during this periodic check. As with all logs, calibrations are performed before and after the survey and added along with the master calibration results to the log.